There's a unit of distance that sounds like it belongs in science fiction: the parsec. You might remember Han Solo bragging about making the Kessel Run in less than 12 parsecs. But here's the thing: a parsec isn't some made up measurement from a galaxy far, far away. It's real, and it's stranger than anything fiction could invent. Because a parsec isn't based on how far light travels or how many meters you can stack end to end. It's based on an optical illusion, a trick of perspective that happens when you look at stars from different sides of Earth's orbit. And when you truly understand what a parsec represents, when you grasp the geometry and the history and the sheer audacity of measuring distances this way, it changes how you see the universe itself. Before we dive in, if you find these kinds of deep explorations fascinating, a quick like or subscribe would really help the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me show you something remarkable. Something so simple that children discover it by accident, yet so profound that it unlocked the true scale of the universe. Hold your thumb out at arm's length. Look at it against the background of the room around you. Now close your left eye and notice where your thumb appears relative to objects behind it. Maybe it lines up with a door frame or the edge of a window, or some object on a shelf across the room. Now switch, open your left eye and close your right. Watch what happens. Your thumb jumps. It shifts position against the background. It might now line up with something completely different. A lamp that was to the left is now to the right. The door frame that was behind your thumb is now beside it. Yet your thumb hasn't moved at all. Your arm is still extended. Your hand is perfectly still. The jump is an illusion, a trick of perspective created by the fact that your two eyes see the world from slightly different positions. This phenomenon is called parallax, and it's one of the most fundamental optical effects in existence. It's also the key that unlocked our ability to measure distances across the cosmos. Everything we know about how far away the stars are, how big galaxies are, how vast the observable universe truly is, all of it traces back to this simple effect you just demonstrated with your own thumb. The parallax effect happens because your two eyes are separated by a few inches. The average distance between human eyes is about 2.5 inches, roughly 6.5 centimeters. That small separation means your left eye and your right eye see the world from slightly different angles. They capture slightly different views of reality. Your brain normally combines these two views automatically, fusing them into a single three-dimensional perception that gives you depth vision. This is why you can judge distances, catch thrown objects, and navigate the world without bumping into things. Your brain uses the difference between what your two eyes see to calculate how far away objects are. Here's the crucial insight. The amount of apparent shift, the size of the jump your thumb makes when you switch eyes, depends on how far away the object is. Hold your thumb very close to your face, just a few inches away, and switch eyes. The jump is dramatic. Your thumb might appear to move several inches against the background. Now extend your arm fully and try again. The jump is smaller. Now look at something across the room, a lamp or a picture on the wall, and switch eyes. The shift is barely noticeable. Look at something outside your window, a tree or a distant building. There's essentially no detectable shift at all. This relationship is consistent and mathematical. Closer objects show larger parallax shifts. Distant objects show smaller shifts. If you know the separation between your two viewing positions and you measure the angular shift of an object, you can calculate exactly how far away that object is. It's basic trigonometry, the kind of geometry the students learn in high school. Nothing fancy, nothing mysterious, just triangles. Ancient civilizations understood this principle. Greek mathematicians and astronomers knew about parallax over 2,000 years ago. They used it to estimate distances to nearby landmarks. They understood that if you stood at two different positions and measured the angle to some distant object, you could calculate how far away it was. Surveyors used this technique to measure the width of rivers without having to cross them. Military commanders used it to estimate distances to enemy fortifications. It was practical geometry with real-world applications. But here's where things get interesting. If parallax works for your thumb against the wall across the room, and if it works for surveyors measuring distances to mountains, shouldn't it work for measuring distances to the stars? Shouldn't astronomers be able to measure how much nearby stars appear to shift against the backdrop of more distant stars, and use that shift to calculate how far away those nearby stars are? The answer is yes. In principle, stellar parallax should work exactly like any other parallax measurement. The geometry is identical. The mathematics is the same. There's no physical reason why it shouldn't work for stars, just as well as it works for your thumb. But in practice, detecting stellar parallax proved to be one of the most difficult challenges in the history of astronomy. For over 2,000 years, from the time of the ancient Greeks until the early 19th century, astronomers searched for stellar parallax and consistently failed to find it. Generation after generation of observers looked for the telltale shift that would prove stars were at measurable distances, and generation after generation came up empty. To understand why this was so difficult, you need to understand what Earth does during a year. Earth orbits the Sun. This isn't controversial today, but for most of human history, it was hotly debated. In January, Earth is on one side of its orbit around the Sun. 6 months later, in July, Earth has traveled halfway around its orbital path and sits on the opposite side. The distance Earth travels during those 6 months is enormous by any human standard. Earth moves about 186 million miles, roughly 300 million kilometers, from one side of its orbit to the other. That's a baseline. In parallax terms, a baseline is the distance between your two viewing positions. When you switched eyes while looking at your thumb, your baseline was about 2.5 inches, the separation between your eyes. When astronomers try to measure stellar parallax, their baseline is the diameter of Earth's orbit, nearly 300 million kilometers. That's an incomprehensibly larger baseline. Surely, with such an enormous baseline, the apparent shift of nearby stars should be easy to detect. Ancient astronomers reasoned exactly this way. If Earth really moves around the Sun, as some Greek thinkers proposed, then the stars should show parallax. We should see nearby stars shifting back and forth against more distant background stars as Earth moves from one side of its orbit to the other over the course of a year. The shift might be small, but it should be there. So they looked, and they found nothing. This was a serious problem. The lack of detectable stellar parallax was used as a powerful argument against the idea that Earth moves. If Earth really orbited the Sun, critics argued, we would see stellar parallax. We don't see stellar parallax. Therefore, Earth doesn't move. The logic seemed airtight. When Nicholas Copernicus published his heliocentric model in 1543, proposing that Earth and the other planets orbit the Sun rather than everything orbiting Earth. The absence of stellar parallax was one of the strongest objections raised against his theory. How could Earth be moving through space at tremendous speed if the stars showed no shift whatsoever? Copernicus himself recognized this problem. His answer was that the stars must be incredibly far away. So far away that even with a baseline of 300 million kilometers, the parallax shift was too small to detect. With the instruments of his time, this was a bold claim. Copernicus was essentially arguing that the universe was vastly larger than anyone had previously imagined. The stars weren't just a little beyond the planets. They were incomprehensibly distant. So distant that the entire orbit of Earth, enormous as it seemed, was essentially a point compared to stellar distances. Most people found this hard to accept. It seemed like special pleading, an excuse invented to explain away an inconvenient lack of evidence. The Danish astronomer Tycho Brahe, one of the greatest observational astronomers of the 16th century, explicitly rejected the Copernican model partly because he couldn't detect stellar parallax. Tycho had the best instruments of his era and the most precise measurements anyone had ever made. If anyone could have detected stellar parallax, it would have been him. He concluded that since he couldn't detect it, Earth must not be moving. Tycho was wrong, but his reasoning was sound given what he knew. He simply couldn't imagine that the stars were far enough away to make parallax undetectable with his instruments. The universe was larger than even the greatest astronomer of his age could conceive. And yet, Copernicus was right. The stars really are that far away. The absence of detectable parallax wasn't evidence against Earth's motion. It was evidence of the staggering scale of the universe. But proving this took another 300 years. The 17th, 18th, and early 19th centuries saw a sustained effort to detect stellar parallax. As telescopes improved and measurement techniques became more sophisticated, astronomers grew increasingly confident that they could finally detect the tiny shifts that had eluded their predecessors. One after another, prominent astronomers announced that they had succeeded. And one after another, their claims were disproven or revealed to be measurement errors. The problem was that the shifts they were trying to detect were almost unimaginably small. To understand just how small, let me give you some perspective. Astronomers measure tiny angles using units called arcseconds. A full circle contains 360 degrees. Each degree is divided into 60 arc minutes. Each arc minute is divided into 60 arc seconds. So one arc second is 1/3600th of a single degree. The full moon, when you see it in the night sky, appears to be about half a degree across, or about 30 arc minutes. One arc second is 1/60th of one arc minute. Imagine dividing the diameter of the full moon into 1800 equal slices. Each slice would be about 1 arc second wide. This is the scale of measurement astronomers were attempting. And they had to do it without modern computers, without electronic sensors, without any of the technology we take for granted today. They had to do it by peering through telescopes, manually reading graduations on measuring instruments, and carefully recording their observations by hand. The challenge wasn't just the smallness of the angles. There were numerous sources of error that could easily overwhelm the tiny signal they were looking for. Earth's atmosphere constantly distorts starlight, making stars appear to wobble and shift position slightly from moment to moment. Temperature changes cause telescope components to expand and contract. introducing subtle movements that could be mistaken for stellar parallax. Even the bending of starlight as it passes through Earth's atmosphere at different angles during different seasons could produce apparent shifts that mimicked parallax. All of these effects were often larger than the actual parallax shift of even the nearest stars. It was like trying to hear a whisper in a thunderstorm. The signal was there, but it was buried under noise from every direction. The frustration must have been immense. Astronomers knew the signal should exist. The geometry was clear. If Earth moved, parallax must be present. But every claim detection fell apart under scrutiny. James Bradley, the Astronomer Royal of England, spent years searching for stellar parallax in the 1720s. He didn't find it, but his careful observations led to the discovery of stellar aberration, a different effect caused by Earth's motion. This proved Earth was moving, but it still didn't reveal how far away the stars were. William Herschel, the discoverer of Uranus, attempted parallax measurements of several stars. He failed to detect parallax, but made other important discoveries along the way. The search for stellar parallax was like a gold rush that kept turning up silver. Valuable, but not the treasure astronomers were seeking. Then came Friedrich Wilhelm Bessel. Bessel was born in 1784 in Minden, a city in what is now northwestern Germany. He started his career not as an astronomer, but as an accountant's apprentice. But he had a passion for mathematics and a meticulous attention to detail that would serve him well in his later career. He taught himself astronomy by studying the observations made by earlier astronomers, and he soon began making his own observations of comets. His work impressed established astronomers so much that he was offered a position at Königsberg Observatory, where he would spend most of his career. What set Bessel apart from his predecessors wasn't just skill with instruments or mathematical ability, though he had both in abundance. It was his systematic approach to understanding and eliminating sources of error. Bessel didn't just try to measure stellar parallax. He first tried to understand everything that could possibly affect his measurements. He studied how temperature changes distorted his instruments. He calculated how atmospheric refraction bent starlight at different altitudes. He developed mathematical techniques to separate true stellar motion from apparent motion caused by Earth's movement and other effects. This approach was revolutionary. Earlier astronomers had often been overconfident in their measurements, announcing the detection of parallax without adequately considering all the ways their observations could be wrong. Bessel was more cautious. He spent years characterizing every possible source of error before attempting the actual measurement. He also chose his target star carefully. Rather than picking the brightest stars in the sky, which earlier astronomers had often done, Bessel selected a relatively dim star called 61 Cygni in the constellation Cygnus the Swan. This star had been noticed decades earlier because of its unusually high proper motion. Proper motion is the actual movement of a star through space relative to more distant background stars. Most stars appear essentially stationary over human timescales because they're so far away that their actual motion is imperceptible. But a few stars, including 61 Cygni, show measurable drift across the sky over years and decades. Bessel reasoned that high proper motion might indicate a relatively nearby star. Think about it this way. When you're in a moving car, nearby objects like fence posts appear to whip past quickly, while distant objects like mountains appear to move slowly. The same principle applies to stars. A star that's moving through space at a given velocity will show more apparent motion across our sky if it's close than if it's far away. So a star with high proper motion is likely to be relatively nearby. This was clever target selection. By choosing a star that was probably nearby, Bessel maximized his chances of detecting a measurable parallax shift. A more distant star might have a parallax too small to detect even with his improved techniques. Bessel began his observations in 1834 using a heliometer, a specialized telescope designed for making precise angular measurements. He observed 61 Cygni systematically, recording its position relative to background stars over many months. He accounted for every known source of error. He corrected for atmospheric refraction. He tracked temperature variations. He monitored the stability of his instrument. Month after month, he accumulated data. In 1838, after more than a year of painstaking observations, Bessel announced his results. He had detected the parallax of 61 Cygni. The star showed an apparent shift of approximately 0.31 arcseconds as Earth moved from one side of its orbit to the other over the course of a year. 0.31 arcseconds. That's about 1/6000th of the moon's apparent diameter. It's an angle so small that a human hair held at arm's length would easily cover it. It's an angle so small that atmospheric distortion, instrument flexure, and countless other effects routinely produce larger apparent shifts. The fact that Bessel managed to extract this tiny signal from all the noise was a triumph of patience, precision, and systematic methodology. Using basic trigonometry, Bessel calculated the distance to 61 Cygni. If the star showed a parallax of 0.31 arcseconds from a baseline equal to the radius of Earth's orbit, then the star must be at a specific distance that could be calculated from the geometry of the situation. Bessel found that 61 Cygni was about 10.3 light-years away. 10.3 light-years, let that sink in. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. In a single year, light covers nearly 6 trillion miles. 61 Cygni was over 10 times that distance, away. About 60 trillion miles. About 100 trillion kilometers. This was the first time in human history that we had a reliable measurement of the distance to any star other than our own sun. For the first time, we knew how far away the stars truly were, and the answer was staggering. The universe wasn't just big, it was incomprehensibly vast. The stars that appeared as points of light in the night sky, the same stars humans had gazed at for tens of thousands of years, were so far away that even traveling at the speed of light, the fastest possible speed in the universe, would take years to reach even the nearest ones. Copernicus had been vindicated. The reason no one had detected stellar parallax for over 2,000 years wasn't because Earth didn't move. It was because the stars were so incredibly distant that even a 300 million kilometer baseline produced a shift of less than 1 arcsecond. The instruments of earlier generations simply couldn't measure such tiny angles. The scale of the universe had exceeded human imagination. The news spread rapidly through the scientific community. Bessel's announcement was a sensation. After centuries of failure, someone had finally succeeded. The distances to the stars were no longer a matter of speculation or philosophical argument. They could be measured. They could be known. Within months of Bessel's announcement, other astronomers confirmed his results and extended them. Thomas Henderson working in South Africa, announced that he had measured the parallax of Alpha Centauri, a bright star visible from the southern hemisphere. His measurements showed that Alpha Centauri was even closer than 61 Cygni, only about 4 light-years away. Friedrich Georg Wilhelm von Struve, working in Russia, measured the parallax of Vega, one of the brightest stars in the northern sky. Interestingly, Henderson had actually made his measurements before Bessel, during observations in 1832 and 1833 at the Cape of Good Hope. But he had been cautious, uncertain of his results, and delayed publishing. By the time he announced his findings, Bessel had already claimed priority. Science often rewards not just discovery, but the confidence to publish. The floodgates had opened. For the first time, humanity could reach out and measure the distances to the stars. The universe had revealed its scale, and astronomers rushed to explore it. But there was a problem with how these distances were being expressed. Different astronomers used different units. Some gave distances in light years, some used miles or kilometers. Some expressed distances in terms of the astronomical unit, the average distance from Earth to the Sun. All of these worked mathematically, but they were awkward. They didn't connect naturally to the measurements astronomers were actually making. Think about what astronomers actually observe when they measure stellar parallax. They don't measure distance directly. They can't stretch a tape measure from Earth to a star. What they measure is an angle. They measure how much a star appears to shift against background stars as Earth moves through its orbit. The distance is then calculated from that angular shift using geometry. It seemed like there should be a unit of distance that connected directly to the angle being measured. A unit where you could take the parallax angle and immediately know the distance without complicated conversions. A unit designed specifically for the task of measuring stellar distances. This is where the parsec enters the story. The term parsec was coined in 1913 by British astronomer Herbert Hall Turner. He was looking for a convenient unit of stellar distance, and he invented a portmanteau combining the words parallax and arcsecond. A parsec, Turner proposed, should be defined as the distance at which a star would show a parallax of exactly 1 arcsecond. This definition is elegant in its simplicity. If you observe a star and measure its parallax to be exactly 1 arcsecond, that star is exactly 1 parsec away. No conversions are needed, no calculations required. The parallax angle directly tells you the distance, but the elegance goes further. The relationship between parallax and distance in parsecs is beautifully simple. Distance in parsecs equals 1 divided by parallax in arcseconds. If a star has a parallax of half an arcsecond, it's 2 parsecs away. If a star has a parallax of 1/10 of an arcsecond, it's 10 parsecs away. If a star has a parallax of 1/100th of an arcsecond, it's 100 parsecs away. This inverse relationship isn't arbitrary. It emerges directly from the geometry of the parallax measurement. The parsec captures the mathematical relationship between angular shift and distance in a single, clean unit. Now, here's something important. No star has a parallax as large as 1 arcsecond. The closest star system to our Sun, the Alpha Centauri system, shows a parallax of only about 0.76 arcseconds. That makes it about 1.3 parsecs away. Proxima Centauri, the closest individual star, has essentially the same parallax since it's part of the same system. Even our nearest stellar neighbor doesn't quite reach the 1 arcsecond threshold. But that doesn't make the parsec impractical. It just means all stellar distances are more than 1 parsec. 61 Cygni, Bessel's historic star, is about 3.5 parsecs away. Sirius, the brightest star in the night sky, is about 2.6 parsecs away. Vega is about 7.7 parsecs away. These are clean, simple numbers that connect directly to the observations astronomers make. 1 parsec works out to about 3.26 light years, or about 30.9 trillion kilometers, or about 19.2 trillion miles, or about 206,000 astronomical units. These are all just conversions. The parsec itself is defined purely geometrically. This geometric definition is why astronomers overwhelmingly prefer parsecs over light years for professional work. When you measure a parallax and want to know the distance, using parsecs gives you the answer immediately. The calculation is trivial. Divide 1 by the parallax in arc seconds, and you have the distance in parsecs. But if you want light years, you need to do the parsec calculation first, and then multiply by 3.26. It's an extra step, and extra steps mean extra opportunities for errors. The parsec is a strange unit. It feels impossible when you first encounter it. A distance based on an optical illusion and an ancient convention for dividing circles. It sounds like something from a bizarre alternate reality. But the parsec is real. It's the standard unit of distance in professional astronomy. And when you understand what it represents, when you grasp the history of how humanity learned to measure the stars, the parsec stops feeling strange. It starts feeling inevitable. The universe revealed its scale through a trick of perspective. Friedrich Bessel detected the tiny shift of a star and proved that the cosmos was vastly larger than anyone had dared imagine. The parsec captures that revelation in a single unit of measurement. The impact of Bessel's discovery extended far beyond astronomy. It changed how people thought about humanity's place in the universe. For millennia, humans had believed they occupied a special place at or near the center of creation. The Earth was the center of the cosmos. The stars were lights on a celestial sphere not far beyond the planets. The universe was cozy, comprehensible, built on a human scale. Copernicus had displaced Earth from the center, putting the sun there instead. But even Copernicus probably didn't imagine how far away the stars truly were. Bessel showed that the stars were suns scattered through an immensity of space that dwarfed anything previously conceived. The solar system, which had seemed so vast when astronomers first grasped its scale, was revealed to be a tiny island in an ocean of emptiness. This was humbling. Some found it terrifying. The philosopher Blaise Pascal had written of the eternal silence of these infinite spaces, filling him with dread. Bessel proved that Pascal's intuition was correct. The spaces between stars were indeed immense beyond imagining. But there was also something exhilarating in this discovery. Humans, with their small telescopes and patient observations, had measured the unmeasurable. They had reached across the void and determined how far away the stars truly were. The universe might be vast, but it was knowable. It took over 2,000 years of effort, from ancient Greek astronomers who searched in vain for stellar parallax, to Bessel's breakthrough in 1838. Centuries of failure followed by a single success that changed everything. The stars were no longer mysteries. Their distances could be measured. Their remoteness could be quantified. And the unit we use to express those distances, the parsec, is a monument to that achievement. It's strange and wonderful and deeply connected to how we came to understand our place in the cosmos. The parsec represents centuries of human effort distilled into a single elegant concept. Every time an astronomer uses it, they're connecting to a tradition that stretches back to ancient stargazers who wondered about the distances to the heavens. The parsec is our answer to their question. Now that you understand how parallax works and how Friedrich Bessel first measured the distance to a star, let's get precise about what a parsec actually is. Because the definition sounds simple when you first hear it, almost deceptively simple. But when you truly understand what's being defined and why, you realize something profound about the relationship between geometry and the cosmos. Let me build up the definition carefully, piece by piece. Start by imagining Earth in its orbit around the Sun. Right now, as you're listening to this, Earth is at some specific point in that orbit. 6 months from now, Earth will have travelled halfway around the Sun and will be on the opposite side of its orbital path. The distance between where Earth is now and where Earth will be in 6 months is about 300 million kilometers. That's the diameter of Earth's orbit, roughly 2 astronomical units. But astronomers don't typically use the full diameter as their baseline for parallax measurements. Instead, they use half of that, the radius of Earth's orbit, which is 1 astronomical unit. There's a technical reason for this. When you measure a star's position from Earth, you're measuring the angle between the star and the Sun as seen from your position. This angle changes as Earth moves, and the way astronomers define parallax uses the Earth-Sun distance as the reference baseline rather than the full orbital diameter. So here's the setup. You have Earth at some point in its orbit. You have the Sun at the center of that orbit, and you have a distant star somewhere out in space. The parallax angle is defined as the angle at the star in the triangle formed by the star, the Sun, and Earth. It's essentially measuring how much the star appears to shift when viewed from Earth compared to where it would appear if viewed from the Sun. A parsec is then defined as the distance at which a star would show a parallax angle of exactly 1 arcsecond. That's it. That's the complete definition. The distance at which parallax equals 1 arcsecond. Now, let me give you some fresh ways to visualize just how small an arcsecond actually is, beyond what we discussed in part 1. Consider a standard pencil about 7 millimeters in diameter. 1 arcsecond is approximately the angle that pencil would subtend if you placed it 1.5 kilometers away, nearly a mile distant. At that range, the pencil would be completely invisible to your naked eye, far too small to detect. But if you had perfect vision and perfect instruments, you could in principle measure its angular size as about 1 arcsecond. Here's another way to grasp this scale. Commercial aircraft typically cruise at about 10 kilometers altitude. 1 arcsecond is roughly the angle subtended by a tennis ball seen from a plane at cruising altitude. You're looking down from 30,000 feet, and somewhere on the ground is a tennis ball. The angle it takes up in your field of view is about 1 arcsecond. Or consider this. The International Space Station orbits at about 400 kilometers above Earth. 1 arcsecond is approximately the angle subtended by an astronaut's helmet viewed from the ground while the station passes overhead. The helmet is about 30 centimeters across. From 400 kilometers away, it spans roughly 1 arcsecond. These examples should reinforce just how extraordinarily tiny the angles are that astronomers measure when they detect stellar parallax. And remember, Bessel's measurement of 61 Cygni showed a parallax of only about 0.31 arcseconds. Less than 1/3 of these already minuscule angles. The precision required to measure such small angles is staggering. Consider what it means to measure something to within a fraction of an arcsecond. You need to know the position of your telescope to extraordinary precision. You need to understand how the atmosphere bends light at different altitudes and temperatures. You need to account for the flexure of your instrument as it tracks across the sky. You need to eliminate dozens of systematic errors, any one of which could produce apparent shifts larger than the parallax you're trying to measure. This is why stellar parallax was the last major prediction of the heliocentric model to be confirmed. The technology simply didn't exist to measure such tiny angles until the 19th century. And even then, it required an astronomer of Bessel's caliber, with his obsessive attention to systematic errors, to finally succeed. Now, let's explore the mathematical relationship between parallax and distance, because this is where the elegance of the parsec truly shines. The formula is beautifully simple. Distance in parsecs equals 1 divided by parallax in arcseconds. That's the entire calculation. 1 divided by the parallax angle gives you the distance. If a star has a parallax of 1 arcsecond, it's 1 parsec away. If a star has a parallax of half an arcsecond, which is 0.5 arcseconds, then 1 divided by 0.5 equals 2. So the star is 2 parsecs away. If a star has a parallax of 1/10 of an arcsecond, which is 0.1 arcseconds, then 1 divided by 0.1 equals 10, so the star is 10 parsecs away. This inverse relationship emerges directly from the geometry of the situation. When you have a triangle with a very small angle at one vertex, the side opposite that small angle is essentially proportional to 1 over the angle itself for small angles measured in appropriate units. The parsec is defined so that when the angle is measured in arcseconds, the proportionality constant becomes exactly 1. No unit conversions, no multiplication factors, just simple division. Let me emphasize what a remarkable simplification this is. In most scientific calculations, unit conversions are a constant nuisance. You have to remember whether to multiply or divide. You have to look up conversion factors. You have to keep track of which units you start with and which units you need to end up with. Errors in unit conversion have crashed spacecraft and caused engineering disasters. But with parsecs, the conversion from parallax to distance is essentially automatic. The unit system is designed so that the numbers just work. This wasn't an accident. Herbert Hall Turner, who coined the term parsec in 1913, was explicitly looking for a unit that would make astronomical calculations easier. He succeeded beyond what he might have imagined. This is why astronomers love parsecs. When you're working with parallax data, which is what you actually measure when determining stellar distances, the conversion to parsecs is trivial. You look up the parallax of a star in arcseconds, you divide 1 by that number, and you have the distance in parsecs. The calculation takes seconds and introduces no rounding errors from conversion factors. Compare this to calculating distance in light years. If you want to convert parallax to distance in light years, you can't do it directly. You first have to calculate the distance in parsecs using the simple formula, then multiply by 3.26 to convert to light years. It's not a difficult calculation, but it's an extra step. And that extra step introduces a source of potential error. The number 3.26 is actually an approximation. The exact conversion factor is closer to 3.26156, and using the rounded value introduces small errors that can accumulate in complex calculations. But the advantages of parsecs go far beyond simple parallax conversions. Many fundamental astronomical formulas work more cleanly when distances are expressed in parsecs rather than light years. Let me give you some specific examples that illustrate why parsecs have become the professional standard. Astronomers often need to calculate how bright a star would appear if it were at a standard reference distance. This allows them to compare the true luminosities of different stars regardless of how far away each star happens to be. The standard reference distance astronomers use is 10 parsecs. A star's absolute magnitude is defined as the apparent magnitude it would have if placed at a distance of exactly 10 parsecs from Earth. The formula connecting apparent magnitude, absolute magnitude, and distance is called the distance modulus equation. It states that the apparent magnitude minus the absolute magnitude equals 5 times the logarithm of the distance in parsecs, minus 5. Notice how cleanly this works. The 10 parsec reference distance, combined with the base 10 logarithm and the factor of 5, produces a formula where the numbers just work out elegantly. If you wanted to use light years instead, you'd need to include additional conversion factors that would clutter the formula and introduce more opportunities for computational errors. Similarly, when astronomers calculate stellar luminosity from apparent brightness and distance, parsecs simplify the mathematics. The luminosity of a star in solar units can be calculated directly from its absolute magnitude, which itself depends on distance in parsecs. The entire chain of calculations flows smoothly when parsecs are the base unit. The Hubble constant, which describes the rate at which the universe is expanding, is conventionally expressed in units of kilometers per second per megaparsec. Megaparsec is 1 million parsecs. The Hubble constant tells you that for every megaparsec of distance, galaxies recede from us an additional 70 or so kilometers per second, due to the expansion of space. Using parsecs here makes the numbers manageable and the physics transparent. There's another reason astronomers prefer parsecs that's worth understanding. When you're doing research, you often need to combine measurements from different sources. Parallax catalogs, spectroscopic surveys, photometric studies. If everyone used different distance units, combining these datasets would be a nightmare of conversions. By standardizing on parsecs, astronomers can share data seamlessly. A distance measurement in one paper can be plugged directly into equations from another paper. The entire field speaks the same language. Even in stellar dynamics, parsecs prove their worth. The mass of the Milky Way's central black hole, Sagittarius a star, was determined by tracking stars orbiting close to it. Those orbital calculations use distances in parsecs because the gravitational equations work more naturally in those units. Consider also the study of star clusters. When astronomers analyze the Hertzsprung-Russell diagram of a cluster, plotting stellar brightness against temperature, they need to know the distance to the cluster. If the distance is known in parsecs, converting apparent magnitudes to absolute magnitudes is straightforward. The distance modulus formula works directly. No extra conversions required. Or consider the study of exoplanets. When astronomers measure the transit of an exoplanet across its host star, they can determine the ratio of the planet's size to the star's size. But to get the actual physical size of the planet, they need to know how big the star is. That requires knowing the star's luminosity, and luminosity calculations are simplest when the star's distance is in parsecs. Let me now convert a parsec to other units so you can appreciate just how large this distance actually is. 1 parsec equals approximately 3.26 light years. Since a light year is about 9.46 trillion kilometers, 1 parsec is about 30.9 trillion kilometers. In miles, that's approximately 19.2 trillion miles. If you wanted to express a parsec in terms of astronomical units, the average distance from Earth to the Sun, you'd find that 1 parsec equals about 206,265 astronomical units. That means you'd need to stack the Earth-Sun distance end to end over 200,000 times to span a single parsec. These numbers are hard to grasp because nothing in everyday human experience approaches these scales. The largest distances we encounter in daily life are maybe a few thousand kilometers, the length of a continent or an intercontinental flight. A parsec is roughly 10 billion times larger than that. Even the fastest things humans have built can't make a parsec feel more manageable. The Voyager 1 spacecraft, the most distant human-made object, has been traveling for over 46 years and has covered about 24 billion kilometers. That's impressive, but it's less than 1,000th of a parsec. At its current speed, Voyager 1 would need about 70,000 years to travel 1 parsec. And the nearest star is over 1 parsec away. Light itself, the fastest thing in the universe, takes 3.26 years to travel 1 parsec. When we say that Proxima Centauri is about 1.3 parsecs away, we're saying that light from that star takes about 4.2 years to reach us. This comparison between parsecs and light years raises a question that many people ask. If light years are more intuitive, connecting distance to the familiar concept of time, why don't astronomers just use light years for everything? Why bother with this strange geometric unit that requires explanation? The answer has to do with how science actually works. In professional astronomy, you spend most of your time doing calculations. You're deriving distances from observations, comparing measurements from different sources, propagating uncertainties through chains of equations. In this context, a unit that simplifies calculations is enormously valuable, even if it's less intuitive to explain. Light years have a kind of poetic elegance. When you look at a star 10 light years away, you're seeing light that's 10 years old. There's something profound about that connection between distance and time. But poetry doesn't help when you're trying to calculate the absolute magnitude of a star or determine the mass of a galaxy. The parsec also has historical precedent on its side. When Turner coined the term in 1913, astronomers had been working with parallax measurements for over 7 decades. They were already thinking in terms of arcseconds and fractions of arcseconds. The parsec formalized what was already implicit in their work. It gave a name to a concept they were already using intuitively. Over the following decades, the parsec became increasingly entrenched in astronomical practice. Textbooks were written using parsecs. Formulas were derived assuming distances in parsecs. Databases were built storing distances in parsecs. Professional journals expected distances to be reported in parsecs. Graduate students learned to think in parsecs. At this point, switching to light years would require rewriting a century of accumulated knowledge and retraining generations of astronomers. The parsec is here to stay, and for good reason. Now, let me tell you something surprising about stellar parallaxes. Despite the parsec being defined as the distance at which parallax equals 1 arcsecond, no star in the entire sky has a parallax that large. Not a single one. The nearest star system to our Sun is Alpha Centauri, a triple star system consisting of two sun-like stars orbiting each other, and a small red dwarf called Proxima Centauri that orbits the pair at a great distance. The parallax of this system is about 0.76 arcseconds. That makes it about 1.3 parsecs away. Even the closest stars don't reach the 1 arcsecond threshold. Barnard's star, the second closest star system after Alpha Centauri, has a parallax of about 0.55 arcseconds. That puts it at about 1.8 parsecs. Barnard's star is famous for having the highest proper motion of any known star. It appears to move across the sky faster than any other star because it's relatively close and happens to be moving through space in a direction that takes it across our line of sight. Sirius, the brightest star in the night sky, has a parallax of about 0.38 arcseconds. That puts it at about 2.6 parsecs. Sirius is so bright, not because it's particularly close, though it is relatively nearby, but because it's intrinsically luminous. It's a hot white star, about twice as massive as our Sun, and about 25 times more luminous. This distinction between apparent brightness and intrinsic luminosity is crucial in astronomy. A star might appear bright because it's close, or because it's genuinely luminous, or both. Without knowing the distance, you can't tell which. Parallax resolves this ambiguity. Once you know the distance to a star, you can calculate its true luminosity from its apparent brightness. This is one reason why parallax measurements are so valuable. They don't just tell you how far away stars are, they tell you what stars actually are. Consider the case of Canopus, the second brightest star in the night sky after Sirius. Canopus has a parallax of only about 0.01 arcseconds, making it about 100 parsecs away. That's roughly 40 times farther than Sirius. Yet, Canopus appears almost as bright as Sirius because it's intrinsically far more luminous. Canopus is a supergiant star over 10,000 times, more luminous than our Sun. Without parallax measurements, we couldn't know this. We couldn't distinguish between a nearby dim star and a distant brilliant one. As you look at more distant stars, the parallaxes become progressively smaller and harder to measure. A star at 10 parsecs shows a parallax of just 1/10 of an arcsecond, or 100 milliarcseconds. A star at 100 parsecs shows a parallax of only 10 milliarcseconds. A star at 1000 parsecs shows a parallax of just 1 milliarcsecond. For most of astronomical history, reliable parallax measurements were limited to stars within about 100 parsecs. Beyond that distance, the parallax angles became so small that measurement uncertainties overwhelmed the signal. Ground-based telescopes had to contend with atmospheric turbulence, which makes stars appear to twinkle and shift position randomly on timescales of milliseconds. This atmospheric seeing limited how precisely stellar positions could be measured. This limitation shaped the history of astronomy for over a century after Bessel's breakthrough. Astronomers could map the immediate solar neighborhood with confidence. They could measure distances to a few hundred of the nearest stars, but the vast majority of the Milky Way remained unmapped. Astronomers could see millions of stars through their telescopes, but they couldn't determine how far away most of them were. This was enormously frustrating. Imagine being able to see a great forest stretching to the horizon, but only being able to measure the distances to trees within arm's reach. You could tell the forest was vast, but you couldn't map its true extent. That was the situation astronomers faced for generations. The Milky Way was clearly enormous, stretching as a river of light across the sky. but its actual size remained uncertain because parallax could only reach a tiny fraction of its stars. Some astronomers tried to estimate distances using the apparent brightness of stars, assuming that dimmer stars were simply farther away. But this approach was fraught with problems. Stars vary enormously in their intrinsic luminosity. A dim star might be a nearby red dwarf or a distant giant. Without some way to determine intrinsic brightness independently, apparent brightness alone couldn't reveal distance. The confusion was profound, and it persisted until other distance methods were developed. This limitation is crucial to understand. It's why astronomers needed to develop other methods for measuring cosmic distances, methods that could reach beyond what parallax alone could measure. The parsec remains the foundation, but the edifice built upon it extends far beyond parallax's reach. Let me share what I find most philosophically striking about the parsec as a unit. The parsec emerges from a fascinating interplay between human convention and cosmic reality. The arcsecond, that tiny angular unit at the heart of the parsec's definition, traces back to ancient Babylonian mathematics. The Babylonians used a base 60 number system, which is why we have 60 seconds in a minute and 60 minutes in a degree. They chose to divide circles into 360 degrees, probably because that number is close to the number of days in a year and has many convenient divisors for calculation. There's nothing fundamental about these choices. 60 and 360 are arbitrary numbers, historical accidents preserved through millennia of mathematical tradition. The arcsecond is a purely human construct, and yet when you combine this arbitrary angular unit with the physical baseline of Earth's orbit around the Sun, using the entirely non-arbitrary laws of geometry, you get the parsec, a unit that works beautifully for measuring stellar distances, a unit that has become the professional standard throughout astronomy. The universe doesn't care about our conventions. The cosmos doesn't know what an arcsecond is. And yet, when we use our conventions to measure the universe, we discover truths that exist independently of those conventions. The distance to Alpha Centauri doesn't depend on whether we measure it in parsecs, light years, or kilometers. It's about 40 trillion kilometers regardless of what units we use. The physical fact exists independently of our measurement systems. Our units are just different languages for expressing the same underlying reality. This is the power of mathematics. Our notational choices are arbitrary, but the relationships we discover are not. The geometry of triangles is the same whether we measure angles in degrees, radians, or some other system. The proportions don't change. The relationships are invariant. When astronomers write that a galaxy is 100 megaparsecs away, they're using human conventions to express a cosmic truth. The convention is arbitrary. The truth is not. Some people find it strange that astronomers use parsecs instead of light years. Light years seem more intuitive. They connect distance to time. They tell you how long light takes to travel from a star to your eye. But parsecs tell you something different. They tell you how the universe appears to shift when you change your point of view. They encode the relationship between observation and reality. They capture the geometry of measurement itself. There's also a practical consideration that working scientists appreciate. The parallax method doesn't actually measure distance directly. It measures an angle. The distance is calculated from that angle. If you express your result in parsecs, you're staying close to what you actually measured. If you express your result in light years, you've added an additional calculation that introduces potential for error, and moves you further from the original observation. This matters more than you might initially think. In scientific work, you want to keep track of your uncertainties carefully. When you measure a parallax, you get a value with some measurement uncertainty attached to it. When you convert that to distance in parsecs, the uncertainty propagates straightforwardly through the simple division. When you then convert to light years, you're multiplying by another number, and the uncertainties compound. Staying in parsecs keeps your calculations cleaner. When you say Proxima Centauri is 1.3 parsecs away, you're really saying something about how that star appears from Earth as our planet moves through its orbit. Distance in parsecs is parallax inverted. It's the measurement expressed as a unit. This is why the parsec, strange as it seems, is actually more fundamental than the light year for certain purposes. The light year depends on the speed of light, which is a separate fact about the universe that has to be measured independently. The parsec depends only on geometry, on the relationship between angles and distances that follows necessarily from the nature of triangles. Think about what this means. The parsec is defined without reference to any physical constant that needs to be measured. It's pure geometry. The speed of light could be different, and the light year would change, but the parsec would remain the same. The distance from Earth to the Sun could be different, and the parsec would change, but the definition would remain unchanged. The parsec is a geometric truth wearing astronomical clothes. This is also why the parsec has proven so durable. Units come and go in science. New constants are discovered. Old standards are refined. Measurement systems evolve. But geometry is eternal. The relationship between angles and distances that define the parsec were true in ancient Greece. They're true today. And they'll be true in any civilization that develops astronomy. The parsec, despite its origins in human convention, connects to something timeless. But the parsec has limits. You can only measure parallax for objects close enough to show a detectable shift. As parallax angles get smaller and smaller, measurement uncertainties eventually overwhelm the signal. For most of astronomical history, reliable parallax was limited to stars within about 100 parsecs. To reach further, astronomers needed other methods. They needed ways to estimate distances that didn't rely on detecting the tiny angular shifts of parallax. They needed to build a ladder of techniques, each rung reaching further than the last, that would eventually allow them to measure distances across the entire observable universe. The construction of this ladder is one of the great achievements of 20th century astronomy. It took decades to build, required contributions from astronomers around the world, and transformed our understanding of cosmic scale. But no matter how sophisticated the ladder became, it always rested on the foundation of parallax. And that ladder, the cosmic distance ladder, is built on a foundation of parallax. Every other technique, no matter how sophisticated, is ultimately calibrated against parallax measurements of nearby stars. The parsec, that strange geometric unit, remains at the base of everything we know about cosmic distances. Parallax is remarkable. It's the foundation of everything we know about cosmic distances. That simple geometric principle, the same effect that makes your thumb appear to jump when you switch eyes, unlocked our ability to measure how far away the stars truly are. For the first time in human history, Friedrich Bessel showed us that the universe could be measured. But parallax has a problem. A severe fundamental limitation that becomes obvious as soon as you try to measure the distances to more distant stars. Remember that parallax angles get smaller as distance increases. A star 1 parsec away would show a parallax of 1 arcsecond. A star 10 parsecs away shows a parallax of only 1/10 of an arcsecond. A star 100 parsecs away shows a parallax of just 1/100th of an arcsecond, or 10 milliarc seconds. And as you push further out, the angles keep shrinking. At some point, the parallax angle becomes so small that it's overwhelmed by measurement uncertainties. Earth's atmosphere constantly distorts starlight. Temperature changes cause telescopes to flex and shift. The instruments themselves have limited precision. All of these effects produce apparent stellar movements that can easily exceed the actual parallax shift of distant stars. For most of astronomical history, working from the ground with the best telescopes available, reliable parallax measurements were limited to stars within about 100 parsecs of the Sun. Beyond that distance, the parallax angles became too small to measure with confidence. The uncertainties in the measurements exceeded the signal being measured. 100 parsecs sounds like a lot, and it is, by human standards. 100 parsecs is about 326 light years, roughly 2 quadrillion kilometers. You could fit the Earth-Sun distance into 100 parsecs over 20 million times. But 100 parsecs is nothing on galactic scales. The Milky Way galaxy is about 30,000 parsecs across. The Sun sits about 8,000 parsecs from the galactic center. If you could only measure distances to 100 parsecs, you could only map a tiny bubble around the Sun, less than 1% of the galaxy's diameter. And galaxies beyond our own? The nearest large galaxy, Andromeda, is about 770,000 parsecs away. At that distance, parallax angles are measured in micro-arcseconds, millionths of an arcsecond. For most of history, such measurements were completely impossible. The observable universe extends for about 14 billion parsecs, 14 gigaparsecs. At those distances, parallax angles would be measured in units so small that no telescope ever built, and perhaps no telescope that could ever be built, would detect them. So how do we know how big the universe is? How do we know that Andromeda is 770,000 parsecs away? How do we know the observable universe spans 14 gigaparsecs? If parallax can only reach 100 parsecs, how did astronomers measure anything beyond that? The answer is one of the most ingenious constructions in all of science. It's called the cosmic distance ladder, and understanding how it works reveals just how clever humans can be when confronted with seemingly impossible problems. The cosmic distance ladder is a series of techniques, each one building on the previous, that allows astronomers to measure progressively larger distances. Parallax forms the bottom rung. It's the foundation, the technique that directly measures distance using geometry. Everything above parallax is calibrated against it. Every higher rung depends on the rungs below. The first step up the ladder uses something astronomers call standard candles. The concept is simple and intuitive. Imagine you're driving at night and you see headlights in the distance. You know roughly how bright car headlights are because you've seen them up close. So if you see headlights that appear dim, you know the car is far away. If you see headlights that appear bright, the car is nearby. You're using the known brightness of headlights to estimate distance. Standard candles work the same way. If you know how intrinsically bright an astronomical object is, and you measure how bright it appears from Earth, you can calculate how far away it must be. Light spreads out as it travels through space. The further light travels, the more it spreads, and the dimmer the source appears. This relationship follows a precise mathematical law called the inverse square law. Double the distance and the apparent brightness drops to 1/4. Triple the distance and it drops to 1/9. The math is clean and predictable. The challenge is finding astronomical objects whose intrinsic brightness you actually know. You can't just assume all stars are equally bright. They're not. Some stars are intrinsically luminous, putting out thousands of times more light than the sun. Others are dim, barely visible even from close up. Just because a star appears bright in our sky doesn't mean it's close. What astronomers needed was a class of objects whose intrinsic brightness could be determined from other properties. Objects where you could look at them, measure something about them, and know how bright they really were. Enter Henrietta Swan Leavitt. Leavitt was an American astronomer working at Harvard College Observatory in the early 20th century. At the time, Harvard employed numerous women as computers, workers who performed tedious calculations and examined photographic plates looking for interesting objects. The women were paid less than male astronomers and often weren't given credit for their discoveries, but they made fundamental contributions to astronomy nonetheless. Leavitt was assigned to study variable stars whose brightness changes over time. She focused particularly on a class called Cepheid variables, named after the prototype star Delta Cephei. These stars pulsate, growing larger and smaller, brighter and dimmer, over regular periods ranging from a few days to several weeks. Leavitt studied Cepheids in the Small Magellanic Cloud, a small galaxy visible from the southern hemisphere that we now know is a satellite of the Milky Way. In 1912, she published a discovery that would transform astronomy. She found that brighter Cepheids pulsate more slowly than dimmer ones. The longer a Cepheid's period, the more luminous it is. This period luminosity relationship was remarkably consistent. By measuring how long a Cepheid takes to complete one pulsation cycle, you could determine its intrinsic brightness. Think about what this means. You observe a Cepheid variable star. You watch it brighten and dim over days or weeks. You measure its period. From that period, you can calculate how intrinsically bright the star actually is. Then you compare this intrinsic brightness to how bright the star appears in your telescope. From the difference, you calculate the distance. Suddenly, astronomers had a way to measure distances far beyond the reach of parallax. Cepheid variables are giant stars, much larger and more luminous than our sun. They can be seen with telescopes even when they're in other galaxies, millions of parsecs away. But there was a critical catch. To use the period luminosity relationship, you need to know not just that longer period Cepheids are brighter, but exactly how much brighter. You need to calibrate the relationship. You need to know that, say, a Cepheid with a 10-day period has an intrinsic luminosity of such and such, while a Cepheid with a 30-day period has a different specific luminosity. How do you calibrate this? You need to know the actual distances to some Cepheids. And the only way to know actual distances is through parallax. This is why parallax is the foundation of the distance ladder. Before you can use Cepheids as standard candles, you have to measure the parallax of nearby Cepheids to calibrate the period luminosity relationship. The Cepheid technique doesn't replace parallax. It extends parallax. It takes the distances measured by parallax and uses them to calibrate a technique that can reach further. For decades, calibrating the Cepheid relationship was difficult because most Cepheids are far away. The nearest Cepheids are several hundred parsecs distant, at the edge of what ground-based parallax could reliably measure. The calibration had significant uncertainties, which propagated into uncertainties in every distance measured using Cepheids. Once Cepheids gave astronomers the ability to measure distances of millions of parsecs, they could reach other galaxies. They could see Cepheids in Andromeda, in galaxies throughout the local group, in galaxies dozens of megaparsecs away. But Cepheids, luminous as they are, eventually become too faint to detect. At distances of perhaps 100 megaparsecs, even Cepheids fade below detectability. To reach further still, astronomers needed an even brighter standard candle. They found it in one of the most violent events in the cosmos. Type 1, a supernovae. A supernova is an exploding star. When certain types of stars exhaust their nuclear fuel, they can collapse and explode with tremendous violence, briefly outshining entire galaxies containing hundreds of billions of stars. For a few weeks, a single exploding star produces more light than everything else in its galaxy combined. There are different types of supernovae, classified by their spectra and light curves. Type 1 supernovae are special because they occur through a very specific mechanism that produces remarkably consistent explosions. Here's how it works. A white dwarf is the remnant core of a dead star, about the size of Earth but containing perhaps the mass of the Sun. White dwarfs are incredibly dense and are stabilized against gravitational collapse by quantum mechanical pressure. But there's a limit to how much mass a white dwarf can have and remain stable. This limit, called the Chandrasekhar limit, after the physicist who calculated it, is about 1.4 times the mass of the Sun. If a white dwarf gains mass beyond this limit, the quantum pressure can no longer support it against gravity. In binary star systems, where two stars orbit each other, a white dwarf can sometimes steal mass from its companion star. Gas from the companion streams onto the white dwarf, slowly adding to its mass. If the white dwarf approaches the Chandrasekhar limit, something dramatic happens. The extreme density and temperature trigger runaway nuclear fusion throughout the entire white dwarf, essentially all at once. The white dwarf doesn't collapse into a neutron star or black hole. Instead, it explodes completely, converting a significant fraction of its mass into energy. The explosion is catastrophic and total. Nothing remains but an expanding cloud of debris. Because all Type 1 supernovae occur at essentially the same mass, the Chandrasekhar limit, they all produce essentially the same amount of energy. They all reach essentially the same peak brightness. Not exactly the same, there's some variation, but the variation is small and can be corrected for using other observations. This consistency makes Type 1 supernovae extraordinary standard candles. When you see a Type 1 supernova in a distant galaxy, you know approximately how intrinsically bright it is. By measuring how bright it appears, you can calculate its distance. And because Type 1 supernovae are so incredibly luminous, outshining entire galaxies, they can be detected at distances of billions of parsecs. Type 1 supernovae allowed astronomers to measure distances to the most remote galaxies observable. They became the tool that revealed the size of the cosmos. But again, there's a calibration requirement. To know exactly how bright Type 1 supernovae are intrinsically, astronomers needed to observe them in galaxies whose distances were already known from other methods. They used Cepheids. They found galaxies containing both Cepheids and Type 1 supernovae. The Cepheids gave the distance to the galaxy. The supernova's apparent brightness combined with that known distance, gave its intrinsic brightness. And the Cepheid distances were calibrated using parallax. Everything traces back to parallax. Every rung of the ladder depends on the rungs below. This is the cosmic distance ladder. Parallax measures distances to nearby stars. Parallax calibrates Cepheids. Cepheids measure distances to nearby galaxies. Cepheids calibrate Type 1a supernovae. Supernovae measure distances to the edge of the observable universe. If any rung of the ladder is wrong, everything above it is wrong. If the parallax measurements are off by 10%, the Cepheid calibration is off by 10%, and the supernova distances are off by 10%. Errors propagate upward through the entire structure. This is why improving parallax measurements matters so profoundly. Better parallax doesn't just help us know the distances to nearby stars more precisely. It refines the calibration of Cepheids, which refines the calibration of supernovae, which refines our understanding of the size and age of the entire universe. And this brings us to one of the most important astronomical missions ever flown, the Gaia spacecraft. Gaia was launched by the European Space Agency on December 19, 2013. Its mission was simple in concept, but staggeringly ambitious in execution. Gaia would measure the positions, distances, and motions of stars with a precision far beyond anything previously achieved. Before Gaia, the gold standard for parallax measurements was the Hipparcos satellite. Hipparcos was launched in 1989 and operated until 1993. It was the first space mission dedicated to measuring stellar positions and parallaxes, and it transformed our knowledge of the nearby stellar neighborhood. Hipparcos measured the parallaxes of about 120,000 stars with precisions around 1 millisecond. This allowed reliable distance measurements out to several hundred parsecs, a significant improvement over ground-based observations that were limited by atmospheric effects. Gaia is in an entirely different league, where Hipparcos measured 120,000 stars. Gaia has measured nearly 2 billion, not million, billion, 1.8 billion individual stars, each with measured positions, parallaxes, and proper motions. That's roughly 1% of all the stars in the Milky Way galaxy. Where Hipparcos achieved precisions of about 1 millisecond, Gaia achieves precisions of about 20 to 30 microarcseconds for bright stars. Microarcsecond is 1/1,000,000th of an arcsecond. Gaia is roughly 50 times more precise than Hipparcos. Let me help you understand how precise a microarcsecond is. It's the angle subtended by a human hair seen from a distance of about 40,000 miles. That's roughly 5 times the diameter of Earth. Imagine trying to measure the thickness of a human hair from 5 Earth diameters away. That's the level of precision Gaia achieves. At this precision, Gaia can measure reliable parallaxes for stars throughout much of the Milky Way galaxy. A star at 10,000 parsecs shows a parallax of 100 microarcseconds. That's well within Gaia's measurement capability. Gaia has effectively expanded the parallax horizon from a few hundred parsecs to tens of thousands of parsecs. This has transformed our understanding of the Milky Way. Before Gaia, we knew the general structure of our galaxy, the spiral arms, the central bulge, the disk and halo, but the details were fuzzy. We couldn't see the three-dimensional structure clearly because we didn't know precise distances to most stars. Gaia changed that. The mission has created a three-dimensional map of the galaxy that was simply impossible before. We can now see the spiral arms in 3 dimensions. We can trace streams of stars moving together through the galaxy, remnants of smaller galaxies that the Milky Way has consumed. We can see the disk warping and flaring at its edges. We can identify stars that were born together in clusters that have since dispersed across the sky. One of Gaia's most surprising discoveries has been the extent of galactic archaeology we can now perform. By measuring not just the positions, but the velocities of stars, Gaia has revealed ancient collision events that shaped our galaxy. Streams of stars, remnants of smaller galaxies torn apart by the Milky Way's gravity, snake through our galactic neighborhood. One such stream, called Gaia Enceladus, or the sausage, because of its distinctive shape in velocity space, represents a dwarf galaxy that merged with the Milky Way about 10 billion years ago. We can trace its stellar remains and reconstruct the collision that made our galaxy what it is today. Gaia has also revealed that the Milky Way's disk is not flat but warped, like a vinyl record left in the sun. The outer edges of the disk bend up on one side and down on the other. This warping was suspected before, but Gaia has mapped it in exquisite detail, showing how it changes with distance from the galactic center. Gaia has also revolutionized the calibration of the cosmic distance ladder. Remember that the Cepheid period luminosity relationship needs to be calibrated using parallax measurements of nearby Cepheids. Before Gaia, only a handful of Cepheids were close enough for reliable parallax measurements. The calibration had significant uncertainties. Gaia has measured parallaxes to thousands of Cepheids throughout the Milky Way. The calibration of the period luminosity relationship is now far more precise than ever before. This improvement propagates up the distance ladder. Better Cepheid calibration means better distances to nearby galaxies. Better galaxy distances mean better supernova calibration. Better supernova calibration means better distances to remote galaxies. The ripple effects of Gaia's precision extend to the very edge of the observable universe, but even Gaia has limits. At the most extreme distances, billions of parsecs, parallax is simply not measurable by any conceivable technology. The parallax of an object 1 billion parsecs away would be about 100 trillionth of an arcsecond. That's 100 millionth of a microarcsecond. It's so small that measuring it would require detecting angular shifts smaller than the wavelength of visible light, which is physically meaningless. For the most distant objects, astronomers rely entirely on other methods, and the most important method for truly cosmological distances is redshift. Redshift is the stretching of light to longer wavelengths. When a source of light is moving away from you, the waves get stretched, shifting toward the red end of the spectrum. This is the optical equivalent of the Doppler effect for sound, where the pitch of a siren changes depending on whether the ambulance is approaching or receding. In the 1920s, astronomer Edwin Hubble, using Cepheids to measure distances to nearby galaxies, discovered something remarkable. Almost all galaxies are moving away from us, and the further away a galaxy is, the faster it's receding. This relationship, now called Hubble's law, was the first evidence that the universe is expanding. The expansion isn't caused by galaxies moving through space, it's caused by space itself stretching. As the universe expands, the space between galaxies grows, carrying the galaxies apart. Light traveling through this expanding space gets stretched along with it. The further light has traveled, the more it has been stretched, and the more redshifted it appears. This means that redshift can be used as a distance indicator. measure the redshift of a galaxy's light, and you can estimate how far away it is based on how much the universe has expanded during the time that light has been traveling. But here's the critical point. To convert redshift to distance, you need to know the rate at which the universe is expanding. This rate is quantified by a number called the Hubble constant, usually denoted h0. The Hubble constant tells you how fast galaxies are receding as a function of distance. It's expressed in units of kilometers per second per megaparsec. If the Hubble constant is 70, that means for every megaparsec of distance, galaxies recede at an additional 70 kilometers per second. Notice how the parsec appears in this fundamental cosmological constant. The Hubble constant, which describes the expansion rate of the entire universe, is expressed in terms of megaparsecs. That strange geometric unit, born from the tiny parallax shifts of nearby stars, has become embedded in a description of the cosmos itself. And here's where an interesting scientific puzzle emerges. Different methods of measuring the Hubble constant give slightly different answers. There are two main approaches. The first approach uses the cosmic distance ladder. You measure parallaxes to nearby stars. You use those to calibrate Cepheids. You use Cepheids to measure distances to nearby galaxies. You use those to calibrate Type 1 supernovae. You use supernovae to measure distances to more distant galaxies. You combine distances with redshifts to calculate the Hubble constant. This approach gives a value of about 73 kilometers per second per megaparsec. The second approach uses the cosmic microwave background, the afterglow of the Big Bang. The CMB is light released about 380,000 years after the Big Bang, when the universe first became transparent to radiation. This light has been traveling for nearly 14 billion years and carries information about the early universe encoded in tiny temperature fluctuations across the sky. By analyzing these fluctuations with sophisticated statistical techniques, cosmologists can infer various properties of the universe, including the Hubble constant. This approach gives a value of about 67 kilometers per second per megaparsec. The difference between 67 and 73 might seem small. It's only about 8%, but the measurements are precise enough that this difference is statistically significant. The two approaches disagree by more than 5 standard deviations. In scientific terms, that's a serious discrepancy. This discrepancy is called the Hubble tension, and it's one of the biggest unsolved problems in cosmology today. There are several possible explanations. Maybe there's a systematic error in one of the measurement methods. Perhaps the Cepheid calibration is slightly off, or the supernova analysis contains a subtle bias, or the CMB analysis makes an incorrect assumption. Astronomers have searched for such errors extensively, but haven't found any convincing candidates. Alternatively, maybe both measurements are correct, and the discrepancy is telling us something new about physics. Perhaps the expansion rate of the universe has changed in ways our standard models don't predict. Perhaps there's some form of early dark energy that affected the universe shortly after the Big Bang. Perhaps there are new particles or forces that we haven't discovered yet. No consensus has emerged. The Hubble tension remains an active area of research, with papers appearing regularly proposing various explanations. It's possible that the resolution will come from improved measurements. It's also possible that we're on the verge of discovering new physics. What I find remarkable about the Hubble tension is how it connects the smallest measurements to the largest questions. The precision of parallax measurements to nearby Cepheids, angles measured in micro-arc seconds, affects our understanding of whether the universe contains unknown physics. The tiniest angular shifts of nearby stars are linked to the most fundamental questions about cosmology. Let me give you a sense of the cosmic distances that the distance ladder has revealed, expressed in parsecs. Within 10 parsecs of the Sun, there are approximately 330 known star systems. These are our closest stellar neighbors, well within the range of direct parallax measurement. The famous bright stars of the night sky span a wider range. Vega lies about 7.7 parsecs away. Arcturus sits at about 11.3 parsecs. Aldebaran, the red giant eye of Taurus, is about 20 parsecs distant. Moving further out, we reach objects that required the distance ladder to measure. The Pleiades star cluster lies about 135 parsecs away. The Orion Nebula, that glowing stellar nursery visible in Orion's sword, is about 400 parsecs distant. The center of our Milky Way galaxy lies about 8,000 parsecs from the Sun, with a supermassive black hole containing 4 million solar masses at its heart. Beyond our galaxy, the distances become truly staggering. The Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, lies about 50 kiloparsecs away. The Andromeda Galaxy, the nearest large spiral comparable to our own, sits at about 770 kiloparsecs, nearly a megaparsec distant. The Virgo cluster, the nearest large galaxy cluster, lies about 16.5 megaparsecs away. The Coma cluster sits at about 99 megaparsecs. The Perseus cluster is about 73 megaparsecs distant. At these distances, we're seeing galaxies as they were hundreds of millions of years ago. And the observable universe extends to about 14 gigaparsecs in every direction, the co-moving distance to the cosmic microwave background. This represents the limit of what we can observe, not because there's nothing beyond, but because light from anything farther hasn't had time to reach us since the beginning of the universe. It's worth pausing to appreciate what these numbers mean. The cosmic distance ladder allows us to measure distances spanning 12 orders of magnitude, from 1.3 parsecs to 14 gigaparsecs, from the star next door to the edge of the observable universe, from Bessel's painstaking measurement of a single star to the mapping of the large-scale structure of the cosmos. Each rung of the ladder required ingenuity, persistence, and the contributions of countless astronomers building on each other's work. Henrietta Leavitt, studying variable stars in photographic plates. Edwin Hubble, recognizing the implications of galactic redshifts. Modern astronomers analyzing Type 1 supernovae in distant galaxies. The cosmic distance ladder is a monument to collaborative science spanning generations and continents, from 1.3 parsecs to 14 gigaparsecs. That's a span of about 10 billion, a factor of 10 to the 10th power. And all of these distances can be expressed using the same fundamental unit, the parsec, scaled up with prefixes like kilo, mega, and giga. The cosmic distance ladder, with parallax at its base and ever more sophisticated techniques reaching upward, allows us to measure distances across this entire range. Every measurement, no matter how sophisticated, traces its calibration back down the ladder to the parallax observations that define the parsec. The parsec isn't just an academic unit that astronomers prefer for obscure technical reasons. It's the foundation upon which our entire picture of the cosmos is constructed. We've traveled a long way together. We started with your thumb appearing to jump when you switched eyes, and we've ended up at the edge of the observable universe, 14 gigaparsecs from Earth. We've traced the history of how humanity learned to measure the cosmos, from Friedrich Bessel's breakthrough in 1838 to the Gaia spacecraft mapping nearly 2 billion stars. We've climbed the cosmic distance ladder from parallax to Cepheids to supernovae, each rung extending our reach further into the void. But now I want to step back and ask a different kind of question. Not how do we measure these distances, but what does it mean that we can measure them at all? What do these vast distances tell us about our place in the universe? What does the parsec, that strange geometric unit, reveal about the nature of reality and our ability to comprehend it? Let me start with something that struck me deeply when I first truly understood what a parsec represents. The parsec exists because the universe is comprehensible. Think about what that means. The same geometric principles that work in a classroom, the relationships between angles and distances that any student can learn with a protractor and ruler, extend unchanged to the largest scales imaginable. There's no cosmic limit where geometry stops working. There's no boundary beyond which triangles behave differently. The mathematics of parallax, the simple equation that relates angular shift to distance, works flawlessly whether you're measuring the distance across a room or the distance to a star thousands of light years away. This is not obvious. It didn't have to be this way. We could have lived in a universe where geometric relationships broke down at large scales. We could have lived in a universe where the rules that govern nearby space didn't apply to distant stars. We could have lived in a universe where the cosmos was fundamentally unknowable, where no amount of observation or reasoning could reveal its true nature. But that's not the universe we find ourselves in. The universe we inhabit is one where geometry extends without limit, where triangles work the same way, whether they span a tabletop or span a galaxy, where the same mathematical principles that helped ancient surveyors measure plots of land help modern astronomers measure the distances to quasars billions of parsecs away. This comprehensibility is profound. It means the universe can be known, not just observed, but understood. We can take the mental tools we develop for practical purposes, for building shelters and navigating landscapes and trading goods, and apply them to mapping the cosmos. The geometry that emerged from human needs on Earth turns out to describe the structure of reality at all scales. When Bessel measured the parallax of 61 Cygni in 1838, he wasn't using any mathematics that would have been unfamiliar to ancient Greek geometers. He was using the properties of triangles, the relationships between angles and sides, that Euclid had described over 2,000 years earlier. The only difference was the precision of his instruments and the care of his methodology. The mathematics itself was ancient, and yet that ancient mathematics, developed on a small planet by creatures who couldn't travel more than a few thousand miles from where they were born, turned out to be the key that unlocked the universe. The same geometry that works for measuring fields works for measuring the distances between stars. The same trigonometry that works for navigation works for mapping galaxies. This tells us something important about the relationship between mathematics and reality. Mathematics isn't just a human invention, a game we play with symbols on paper. It's a discovery. The relationships we find in mathematics exist independently of us. They were true before humans evolved, and they'll be true long after we're gone. When we do mathematics, we're not creating something new. We're uncovering something that was always there. The physicist Eugene Wigner wrote a famous essay called "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He marveled at how mathematical structures invented by humans for purely abstract reasons often turn out to describe physical reality with uncanny precision. The parsec is a modest but perfect example of this phenomenon. A unit defined using ancient Babylonian number conventions and the arbitrary choice to divide circles into 360 degrees turns out to be precisely what astronomers need for measuring the cosmos. Why does this work? Why should human mathematical constructs map onto cosmic reality? This is one of the deep mysteries of science. Some philosophers argue that mathematics is discovered, not invented, that mathematical truths exist in some Platonic realm that we access through reason. Others argue that mathematics succeeds because it evolved alongside our physical understanding, shaped by the same reality it describes. The debate continues, but the fact remains: mathematics works, geometry works, the parsec works. Now let me turn to something more sobering: what the parsec reveals about cosmic isolation. The nearest star to our Sun is Proxima Centauri, about 1.3 parsecs away. That's roughly 40 trillion kilometers. 40 trillion. If you could count 1 kilometer per second, it would take you over 1 million years just to count to 40 trillion. And that's the distance to our nearest neighbor. Let me put this in terms of travel. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reaches speeds of about 190 kilometers per second when it's closest to the Sun. At that speed, it would take about 6,700 years to travel 1 parsec. To reach Proxima Centauri at that speed would take about 8,700 years. 8,700 years. The pyramids of Egypt were built about 4,500 years ago. If the ancient Egyptians had launched a spacecraft toward Proxima Centauri, at the time they were building the pyramids, traveling at the fastest speed any human spacecraft has ever achieved, that spacecraft would be less than halfway there today. It would still have thousands of years of travel remaining. And Proxima Centauri is our closest stellar neighbor. Most stars are vastly further away. The Milky Way galaxy is about 30,000 parsecs across. That's roughly 100,000 light years. If you could somehow travel at the speed of light, which no physical object can do, it would take you 100,000 years to cross our galaxy. 100,000 years. Modern humans have only existed for about 300,000 years. Crossing the galaxy, even at light speed, would take a significant fraction of our entire existence as a species. The nearest large galaxy comparable to the Milky Way is Andromeda, about 770 kiloparsecs away. That's 2.5 million light years. The light you see from Andromeda tonight began its journey when our planet was home to Australopithecus, before the emergence of the Homo lineage. That ancient light has been crossing the void between galaxies for longer than our species has existed, and Andromeda is close by cosmic standards. The observable universe extends for 14 gigaparsecs. The most distant objects we can see are so far away that their light has been traveling for over 13 billion years to reach us. When that light began its journey, the Earth didn't exist. The Sun didn't exist. The solar system wouldn't form for another 8 billion years. What does it mean to exist in a universe of such scale? One interpretation, and it's hard to avoid, is that we are profoundly isolated. The distances between stars, let alone between galaxies, are so vast that meaningful contact with any other intelligence seems impossibly difficult. The speed of light, the fastest anything can travel, is far too slow to make interstellar communication practical on human timescales. A message sent to Proxima Centauri would take over 4 years to arrive. A response would take another 4 years to return. That's 8 years for a single exchange. And Proxima Centauri is the closest star. Imagine trying to have a conversation with a civilization in Andromeda. Each message would take 2.5 million years to arrive. By the time they received your message, human civilization as we know it might not exist anymore. By the time their response arrived, whatever sent the original message would be unimaginably different or long gone. The Fermi paradox asks why, in a universe so large and so old, we haven't detected evidence of other technological civilizations. There are many proposed answers. Perhaps life is rare. Perhaps intelligence is rare. Perhaps civilizations tend to destroy themselves before they can spread to the stars. Perhaps they exist, but are deliberately hiding. But one of the simplest answers is just distance. The cosmos is so vast that civilizations might exist in enormous numbers and still never encounter one another. The parsecs between us represent barriers that no technology we can imagine would overcome in practical timeframes. We might be surrounded by intelligent life. There might be civilizations around millions of stars in our galaxy alone. But if they're hundreds or thousands of parsecs away, we might never know they exist. The universe might be teeming with intelligence that remains forever isolated. Islands of consciousness, separated by gulfs of emptiness so vast that no bridge can span them. This is a melancholy thought. But let me offer another perspective, one that I find more hopeful. The fact that we can measure these distances at all is remarkable. Think about what we've accomplished. We are small creatures on a small planet orbiting an ordinary star in an unremarkable region of a typical galaxy. We evolved to survive on African savannas, to hunt and gather, to form social groups and raise children. Our brains developed to solve the problems of survival on a planetary surface, not to comprehend the cosmos. And yet, here we are, discussing distances of billions of parsecs. We have figured out how to measure the universe. We have developed the mathematics, built the instruments, launched the spacecraft, and assembled the understanding necessary to determine that Proxima Centauri is 1.3 parsecs away. That Andromeda is 770 kiloparsecs away. That the observable universe extends for 14 gigaparsecs. For most of human history, the stars were mysteries. Their distances were unknown and unknowable. Ancient people looked up at the night sky and could only wonder. Were the stars nearby lights attached to a celestial sphere just beyond the planets? Were they distant suns scattered through an infinite void? Were they something else entirely? Something beyond human understanding? The question seemed unanswerable. How could anyone possibly measure the distance to a point of light in the sky? There was no road to travel, no surveyor's chain to stretch across the void. The stars were simply there, unreachable and unmeasurable. And then, through patient observation and careful reasoning, we answered the question. Bessel measured the parallax of 61 Cygni and proved that stars were distant suns, trillions of miles away. Henderson measured Alpha Centauri. Struve measured Vega. Within years, the distances to dozens of stars were known. Less than 2 centuries later, the Gaia spacecraft has measured the distances to nearly 2 billion stars with precisions that would have seemed magical to Bessel. We have climbed the cosmic distance ladder rung by rung, each step requiring new insights, new techniques, new technologies, and each step has revealed more of the universe's true scale. We are not passive observers of the cosmos. We are active investigators. We probe its secrets. We measure its dimensions. We map its structure. We have taken the universe, vast and mysterious, and made it knowable. The parsec, that strange unit that sounds like it belongs in science fiction, is a monument to human ingenuity. It represents our ability to take a simple principle, the apparent shift of nearby objects against distant backgrounds, and extend it to measure distances that dwarf anything in human experience. The parsec is not just a unit of distance, it's a symbol of what we can achieve when we combine observation with mathematics, patience with persistence, curiosity with rigor. Think about how unlikely this achievement is. We are biological organisms, products of billions of years of evolution on a single planet. Our brains evolved to track prey animals across savannas, to recognize faces, to navigate social hierarchies. Nothing in our evolutionary history prepared us to think about distances of billions of parsecs or timescales of billions of years, and yet we can do it. We can stretch our minds to encompass the cosmos. We can develop mathematical tools that let us reason about scales utterly unlike anything in our daily experience. We can build instruments that detect the tiny angular shifts of distant stars and use those measurements to map the universe. This is perhaps the most remarkable thing about the parsec. Not that it exists, but that we figured it out. That creatures who evolved to survive on African plains can now measure distances to galaxies billions of parsecs away. The parsec is a monument not just to the universe's comprehensibility, but to humanity's capacity to comprehend. There's something else the parsec teaches us. It teaches us that the universe has structure. The stars are not scattered randomly through space, like grains of sand thrown into the air. They cluster into galaxies, vast collections of billions of stars bound together by gravity. Galaxies cluster into groups and clusters. Clusters arrange themselves into superclusters and filaments. Between these structures are enormous voids, regions of space, hundreds of millions of parsecs across where almost nothing exists. This structure, called the cosmic web, extends across the entire observable universe. Filaments of galaxies stretch for billions of parsecs, connecting dense clusters like strands of a spider's web. The voids between them are not truly empty, but they contain far fewer galaxies than the filaments and clusters. Understanding this structure is one of the great projects of modern astronomy. By measuring distances to millions of galaxies, astronomers have mapped the cosmic web in 3 dimensions. They have identified superclusters and voids. They have traced the filaments that connect them. They have built a picture of the universe's architecture on the largest scales. The names of these structures evoke their grandeur. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, the Boötes Void, the Cold Spot. Each represents a feature in the cosmic web that we can only see because we can measure distances accurately. Without the parsec and the distance ladder built upon it, these structures would be invisible to us, hidden in the chaos of uncalibrated data. The largest structures we've identified span hundreds of megaparsecs. The Hercules Corona Borealis Great Wall, discovered in 2013, stretches about 3 gigaparsecs across. It's the largest known structure in the universe, a vast archipelago of galaxies separated by equally vast voids. And we can only know it exists because we can measure the distances to the galaxies that compose it. All of this depends on being able to measure distances accurately. And every distance measurement, no matter how sophisticated the technique, traces back ultimately to parallax, to the parsec, to that fundamental geometric relationship between angle and distance that Bessel first exploited in 1838. There's one more thing I want to share about the parsec, and it's perhaps the most mind-bending aspect of all. It concerns the relationship between distance and time at cosmic scales. When we measure the parallax of a nearby star, we're measuring where that star appeared to be when the light reaching our telescope left the star. For nearby stars, this distinction is negligible. Light from Proxima Centauri takes about 4 years to reach us. The star doesn't move much in 4 years. The difference between where it was when the light left and where it is now is tiny. But for more distant objects, the distinction becomes significant. Light from Andromeda takes 2.5 million years to reach us. When we look at Andromeda, we're not seeing where it is now. We're seeing where it was 2.5 million years ago. During those 2.5 million years, Andromeda has been moving through space. It's not in the same place anymore. The Andromeda we observe is a ghost, an image from the ancient past. At the largest scales, this becomes even more complicated because the universe is expanding. Space itself is stretching. While light from a distant galaxy travels toward us, the space between us and that galaxy is growing. Consider a galaxy whose light has been traveling for 13 billion years to reach us. You might think that galaxy is 13 billion light years away, but it's not. Due to the expansion of space during those 13 billion years, that galaxy is now much further away than 13 billion light years. It's actually about 46 billion light years away in terms of its current distance from us. This means there are different ways to define distance in cosmology. The look-back distance tells you how long the light has been traveling. The co-moving distance tells you how far away the object would be today if you could somehow measure the distance instantaneously. The angular diameter distance tells you how far away the object would need to be in a non-expanding universe to appear the same angular size. These different distance measures agree for nearby objects, but diverge significantly for objects at cosmological distances. The parsec, defined by parallax, connects most directly to what astronomers call the angular diameter distance. But at the larger scales, where cosmic expansion dominates, the relationship between parallax and distance becomes more complex than the simple formula we discussed earlier. This complexity is not a flaw in the parsec or in our understanding. It's a feature of living in an expanding universe. Distance itself is a richer concept than it appears in everyday life. On Earth, distance is simple. The distance between 2 points is just the length of the path connecting them. But in a universe where space is expanding, where the fabric of reality is stretching, distance becomes more subtle. There are different kinds of distance, different ways of asking how far apart two things are, and they give different answers. The parsec, born from the simple geometry of parallax, leads us into these deep waters. It starts with holding your thumb at arm's length and watching it jump when you switch eyes. It ends with contemplating the expansion of space-time and the nature of distance itself. This is the journey that astronomy offers, from the familiar to the cosmic, from the intuitive to the mind-bending, from everyday experience to the most profound questions about the nature of reality. What other field offers such a journey? Where else can you start with something as simple as your thumb appearing to jump and end with questions about the nature of space-time itself? Astronomy has this unique power to connect the mundane with the magnificent, the everyday with the eternal. The parsec sits at the heart of this journey. It's a humble unit, defined by earthly geometry, yet it reaches out to touch the most distant objects in the observable universe. It was invented to solve a practical problem, making distance calculations easier, yet it embodies profound truths about how we can know the cosmos. The parsec is the bridge that connects these scales. It's a unit that starts with everyday parallax and extends to the structure of the cosmos. It's strange at first, yes. It sounds impossible, but it's real, it's precise, and it's the foundation upon which our entire understanding of cosmic distances is built. Let me close by reflecting on what we've learned. The parsec is approximately 3.26 light years. That's the conversion factor you might see in a textbook. But I hope you now understand that this conversion, while technically correct, misses the point. The parsec isn't defined by its relationship to light years. It's defined by geometry. It's the distance at which a star would show a parallax of 1 arc-second. This definition connects the parsec directly to observation. When astronomers measure parallax and want to know distance, the conversion to parsecs is immediate and trivial. This is why astronomers use parsecs rather than light years. Not because they want to confuse the public, but because parsecs are the natural unit for the measurements they make. The parsec emerged from over 2,000 years of human effort to measure the distances to the stars. Ancient Greeks understood the principle of parallax, but lacked the instruments to detect stellar parallax. Medieval and early modern astronomers searched without success. Finally, in 1838, Bessel succeeded, and in the decades that followed, astronomers developed the cosmic distance ladder, using parallax to calibrate other techniques that could reach further and further into the cosmos. Today, the Gaia spacecraft has measured parallaxes to nearly 2 billion stars, with precisions measured in micro-arcseconds. We have mapped the three-dimensional structure of the Milky Way. We have calibrated the distance ladder with unprecedented accuracy. We can measure distances to galaxies billions of parsecs away. All of this rests on parallax. All of this rests on the parsec. That strange geometric unit, born from an optical illusion and an ancient convention for dividing circles, has become the foundation of cosmic cartography. The universe is vast. The distances are almost incomprehensible. Proxima Centauri at 1.3 parsecs. Andromeda at 770 kiloparsecs. The edge of the observable universe at 14 gigaparsecs. These numbers span a range of over 10 billion from nearby stars to the most distant objects we can see. And yet we know these distances. We have measured them. We have understood them. We have taken the universe, infinite in its mysteries, and made it finite in its measurability. This is one of humanity's greatest achievements. We are small creatures on a small world, evolved to survive in local environments, our brains shaped by the problems of finding food and avoiding predators. And yet, we have figured out how to measure the cosmos. We have extended our reach from the nearby to the infinitely distant. We have built the cosmic distance ladder and climbed it, rung by rung, to the edge of what can be seen. The parsec captures this achievement. It's a unit born from geometry, refined by technology, and extended to the limits of observation. It's strange and wonderful and profound. The next time you look up at the night sky, remember what you now know. Those points of light are distant suns, many of them hundreds or thousands of parsecs away. The light entering your eyes has been traveling for years, or centuries, or millennia. You are seeing into the past, observing the universe as it was long ago. And remember too that we know how far away those stars are. We have measured them. We have understood the geometry of parallax and used it to map the cosmos. We have created the parsec and expressed our measurements in kiloparsecs and megaparsecs and gigaparsecs, revealing a universe of staggering scale. The stars are far away. The galaxies are farther still. The edge of the observable universe lies at distances that defy easy comprehension. But we know these distances, we have figured them out, and that knowledge, earned through centuries of observation and reasoning and technological development, is one of the most remarkable things about being human. We are small, but we can understand the large. We are brief, but we can comprehend the ancient. We are local, but we can know the distant. The parsec makes this possible. That strange unit, born from the geometry of parallax, connects us to the cosmos. It tells us how far away the stars are. It anchors our understanding of cosmic structure. It reminds us that the universe, vast as it is comprehensible. Sleep well tonight knowing that the universe is measurable, that the same geometric principles that govern your classroom govern the cosmos, that the distances to the stars, as vast as they are, can be known. The parsec is not science fiction. It's one of the most remarkable truths about the universe we inhabit, and understanding it connects you to a tradition of inquiry that stretches back thousands of years, to ancient stargazers who wondered about the distances to the heavens, through Bessel's breakthrough, through the development of the cosmic distance ladder, to Gaia mapping billions of stars. You are part of this tradition now. You understand what a parsec is and why it matters. You understand the geometry of parallax and how it reveals cosmic distances. You understand the distance ladder and how each rung depends on the ones below. You've joined the community of people who know how the universe is measured. This knowledge is yours. It connects you to the cosmos and to the long human effort to understand our place within it. The universe is vast beyond comprehension, but it is also knowable, and that makes all the difference. The parsec, that strange unit born from geometry and ancient convention, stands as proof of this knowability. It connects us to the cosmos and reminds us that even the most distant reaches of space can be measured, understood, and mapped by curious minds on a small planet. Good night.